Go for it.
Okay, cool. It's DevOps DC. That's the name of the group, right?
Data Ops DC.
Data Ops. My bad. Data Ops DC. I'm sorry. I actually think sorry about that. Very nice to meet everybody here. Today, I'm going to be talking about the Delta Lake architecture. My name is John O'Dwyer. I'm a developer advocate at Databricks. Just a little bit about myself. I'm developer advocate, as I mentioned. I'm actually pretty new to this job. I was a solutions architect for the last 4 years at Databricks. It's been an incredible ride. I think that everybody here probably knows what Databricks is. I actually started at the company and was a customer before that when no one had any idea who we are. It's been actually incredible to see what has happened over the last 4 years, actually 6 years since I started using Spark. Before that, I was a data scientist. That's where I actually got introduced to Spark and doing ML at scale. Before that, a software developer for my whole career. Then outside of work, I just love being in the mountains with my family. We like to do a lot of biking and skiing. To get into the architecture, probably a good place to start is the transaction logs that are associated to Delta or Delta logs. And actually, before I even jump into this, does anybody have a question? Does everybody know what Delta and Delta Lake is?
Yeah, no. Can you kind of explain that before we jump
Okay.
into this? Yeah.
Yeah, I tell you, and this is actually a good place to start based off of that. But essentially, Delta Lake is an open source technology that's essentially a schema-driven data warehouse table that lives on usually object storage on the cloud, but it can actually be on-prem or other places as well. It's a lot like Parquet. I actually used to describe it as Parquet on steroids. Does everybody know what Parquet is or have an idea of what Parquet is? Would that be a good assumption as a file-based storage format for big data?
It's like an optimized CSV file, basically. That's how I always think of it.
Yes, exactly. I would say the main difference between the main differences between it and CSV are one, that it is optimized both in a compacted way so that it actually can be read into memory a lot more efficiently. But then the other thing is that Parquet itself is a columnar and self-describing format. What I mean by that is if you have, let's say you have CSV files or JSON files, those files, one, they're actually not, they're human readable, so the text is actually more verbose than Parquet. But the other thing is that you actually need to infer the schema by the values that you see instead of it being defined and self-describing in the file format itself. That is the basis for Delta, is Parquet files at its base. You can think of this as, you could think of what you're seeing here as a folder or a set of folders, and think of Parquet as CSV. I won't repeat that. I think that there's people in my company that would yell at me, but you can kind of think as the Parquet piece is like CSV, except for what you're doing is you're actually using some of that self-describing nomenclature in the Parquet file to determine where you're actually putting values. The reason why I describe it as Parquet on steroids is that there's also a transaction log that's associated with these directories and the files themselves. So you can actually read what's in a Delta table just by looking at the Parquet files. But as we'll actually get into a little bit more, you will also see that there's a logging format, and those formats actually describe what's in what files comprise a valid version of the table. It also describes the schema that's involved in that table, and and metrics that are associated with the file, so that you can find and read only the data that you need. And we'll get into some of those pieces as we go. First thing around the logs, and I'll put this back up. This is actually describing the transaction logs here. And one of these, this one is the 0 version. This one is the first version. We'll see that versioning will be continual, and it will actually always tell you where you are in the table at any given time. Thanks for putting both Delta IO and also Parquet, the Apache of Parquet out there too, Banjo. So if we keep going, what you can think of as these versions. So version N or version 1 is essentially version 0 plus some actions. And what those actions are whatever was there before. It's the change in the metadata, also the adding and removing of files. The adding of files is anything that's either appended or updated in the Parquet files, and the removal of files is just that. It's not physically removing them. It's actually in the metadata. It's saying we stopped using Parquet 827 because it has erroneous values or rows that we deleted. We're going to start using 828 now. The result is the comprising of that version plus the extra data, metadata, and the new files that are associated with that version of the table. What this actually allows you to do, one of the really great parts of Delta is the fact that you can, it's atomic. And each one of these versions is a version of the table that is whole at any given time. So this is an example of what version 0 would look like to version 1, where you added 2 Parquet files, and then in version 1 you removed them and added a third Parquet file. There also can be cases where these are together, and you could actually add, you remove 1 and you keep 2 and add a third.
Can we add or delete rows in between?
Yes. Yes, and that's actually a major feature. Sorry, I cut you off though. Do you want to finish that thought, or was that the question?
I just wanted to say, because you said remove 1 and 2 and then add 3. I was just wondering, is it possible to just remove a few rows from 1, or add a few rows to 1 and save that as a commit rather than storing and removing the entire file?
Well, so here's the reason why it actually it's additive. What it's doing is if you removed say 4 rows from what comprised of the first 2 files, And 2 were in, you had 4 rows that you removed and 2 were in the first and 2 were in the second. What you're actually doing is you're then invalidating those files and you're writing a third file that comprises of the 2 together. So and then you're accounting for that in the JSON version of the of that set. So it's actually, and it's not always like, it's not always, and usually will never actually be the full set that you would replace with a new file. It's usually a very small subset where it's, you have billions of rows in a table and you're essentially saying, get rid of one file of thousands and add a new one, whether those are for appends or updates. The reason why it's that way is that the big problem with removing rows in big data, and what this actually takes care of, is the fact that other people can be reading that, and you can corrupt data by changing it while people are actually interacting with it. So what we're doing instead is essentially having a rolling list of everything at all times. There's ways to clean that up as well, and also automatic ways to clean it up too. So you're never going to actually update a file. You're actually going to say, this is the new one and don't worry about that old one for version 2 on. We have something.
Sorry to cut you off. So just understanding. So the advantage of using something like Parquet is that if I've got a huge database, it will actually have a number of files, right? Of let's say 1,000 rows or something. So if I got a change made in one particular row, I will just delete that particular file and replace that with the new version, right?
Well, that's not an advantage of using Parquet, because when you do that, you can actually corrupt that data. It would be an advantage of using Delta for that reason.
Yeah, got it. Thank you.
Okay, cool. So when we're doing this, and this is actually to the point of why you also wouldn't want to actually update one of the existing live files, is that there can be conflicts, and what we're doing is like solving that problem by doing it optimistically. Like essentially somebody is writing an append. If that gets in first, you would essentially, the second user would have to retry until they actually got in. That's essentially what an optimistic conflict resolution is with file structures. The other thing is that this data can be massive, right? We're talking we actually have customers on AWS actually that put in that stream data into these Delta tables over a petabyte a day, which is in a massive amount of data. It's so large that when they actually started doing this, and they were thinking about doing this on-prem, and that this size and scope is actually normal now, but about 3 years ago, we conceived of Delta for a customer that was doing petabyte scale streaming, and the thing is that that amount of data is so massive that it actually isn't very easily done on-prem, and something like S3 is actually extremely great for handling this, because if you tried to put that much information on-prem, you almost need to actually set up a completely new disk structure on-prem every week, so that you can continually do that, like, just racks and racks of computers every week, just to keep up with that amount of scale of writing of data. What also is the case when you actually get to that massive scale, handling the metadata itself actually is can be a massive scale project. And for that, we're actually handling that metadata with Spark. And to stop again, do people here know what Apache Spark is and have used it in the past? Would you like me to describe what that is as well?
Yeah, that's a good high level overview would be good.
Okay, so so Apache Spark is a project that was started. Wow, it's probably 9 or 10 years ago now, and it's a big data technology. It's what most big data it's what most big data now is manipulated and read and written with. It's a clustering technology for data manipulation and reading and writing of data. There's obviously a lot more features off of that, but that's the basis of it. And it's large scale cluster computing. So when you think of if you either need on top of that, it also does advanced analytics, or you can actually break down smaller scale, massive amounts of smaller scale ML and distribute it across a Spark cluster to do all of that work, all that data manipulation and compute all at one time. And that's what it's used for. Is essentially you spin up a Apache Spark cluster. In our case, on Databricks, you would spin that up on Databricks, and it would be a Databricks specific cluster. And that cluster would have a driver, which essentially is handing out tasks and jobs for the workers to do. And it would have a number of workers. Let's say the standard size that we have is usually around 8 workers, and that driver is handing out work for all the workers to do, telling worker 1, go compute this part of the data frame. You compute this part of the data frame. When it's actually all done, it will come back, and then it would be written out somewhere as well. When you're a normal thing to do over the years is to read and write Parquet files. And what we did with Delta was to make the transition to Delta seamless, where it's essentially the same API, except for you're just hitting a Delta table as opposed to Parquet. And Parquet is when you read Parquet with Spark, you're essentially reading thousands of files at one time. All of those files would have potentially be either in a folder or in a usually a partitioned, a columnar partitioned formatted set of folders as well. And that's the same for Delta. So, so that's the basis of how it works, what that logging structure, and also how the mechanism for actually reading and writing and updating data, what that allows you to do, or what that employs is there's pieces and features that allows for. The first being schema and schema enforcement, and also evolution. So I had mentioned before that Parquet is a self-describing file format. Well, which it actually allows you to evolve that file format and change it over the course of time. But the problem is that those files, Parquet can actually evolve in ways that make them incompatible, either corrupting themselves or actually making them incompatible with the overall set. Where you're looking at thousands of files and you change one of those, that can actually corrupt the set as a whole. And what we're doing with Delta is we're enforcing a schema so that that doesn't happen. When you enforce a schema, you also need to be able to allow it to let it evolve correctly as well. So what we mean by schema evolution is, let's say you have a table, a delta table that has column A, B, and C, and you want to have a fourth column called column D, and it will allow you to have that column. It will also it'll also compensate for those for the missing columns in the Parquet files that it didn't have it. It won't actually write it. It will just identify that column does not exist in there, and it will compensate for it when it's looking at you know, thousands or millions of these files at any given time. Before I go on, I want to see if that makes sense, or if anybody has any questions about that. Oh,
I think the question I have is you have the versions, and can different schemas be versioned, or is it always just like one version?
no, it's not only one version. You don't necessarily. I'll show you some stuff in a minute. It's a very good question. You don't necessarily like stamp a version of a schema, but it evolves from a place like, and each version does have an identifiable schema that is associated to it. Does that? I think I kind of answered your question. We'll get into it a little bit more, but is that what you're wondering? Or is it like, were you wondering if you say, boom, version 5, it's going to have X, Y, and Z columns and nothing else? Is that what you mean? Or
Well, I think you answered the question in that there's, it's not binary, it sounds like.
It's not binary. It can be fluid.
Okay.
But it is like, but each version does have an identifiable schema, but it's not like you would necessarily always, like you may not actually, you can actually make it so it does not evolve, but without you knowing. But generally speaking, if you are going to allow it to evolve, it can freely flow as long as the new version does not evolve in an incompatible way. What I mean by that is taking a column that was a string, let's say column B was a string, and you want it to be a decimal, and you know there's words in that column, like that would actually then fail.
Okay, thank you.
Yep. This is actually a newer functionality of Delta tables, and it's a generated column. This is something that has been in the, there is a Databricks flavor that is a little bit more fully functional than the open source version. This has been in Databricks for a couple versions now. I would say 6 months is my guess. And in version 1.0 of Delta, this was added as an experimental an experimental feature, and will become fully featured soon. But the really cool part of this is that you can generate columns off of other columns. What this one case here is showing is that you can actually take event time, and you can cast it as its own date for every column. And essentially you could also then give that column if you wanted, but if you don't, it would actually be derived at all times. The really great part of this, and the reason why this was made anyways, was really this certain use case is something that we see all the time, especially with streaming, logging, and IoT data. So when you think about it, all all like any sort of time series data, it's going to come with a specific event time. But when you actually want to do a partition, you would want to partition that off of something that doesn't have such low cardinality, and you want to do that off of, generally speaking, off of a date is a good way to do that. You could also do that off of you could have this be generated on a month or a year or whatever you wanted as well. So this is actually a pretty, I don't know, something that I find, it's something that like my customers were asking for a long time, and I like to geek out about, so apologies. So the next piece, and this actually comes to your question, TG. If I hope you don't mind me calling you TG, is around time travel and clones. And this is also, when I say time travel, it's actually versioning as well. It's a really cool name for an idea that is not like it's great to have. It's not quite as cool as actually time travel, but what time travel is all of those versions are specific, and there is a specific historical table that is associated with each one of those versions, and each one of those specific tables have metadata that describes the schema, to your point. And you can always go back and find those at any given time. It's really just what is the metadata associated, and also what's the metadata associated, and also what are the files that comprise that table. And you can go back either based off of version, or you can, and this is what I find a little bit more used, is going based off of a timestamp, since version can be pretty esoteric, and you're usually saying what was the version as of midnight at yesterday, and seeing what that was. These are pretty powerful, and for those data scientists in the room, this is these can help with reproducibility of experiments, since data does change, and data does change over time. You can actually reproduce old or historical models based off of the exact data that you actually built those models off of in the first place.
Sort of a different question, but I was just wondering, how is this implemented internally? Do they build it as a virtual file system that has versioning information, or is it as a set of directories and things like that?
This is all actually, so like, let me go back to, sorry. This one is, this number is actually the number that's on that JSON file. If you remember back, and I can actually go back and show you if you want, but the version is actually, it would be, zeros 1071.json would describe what is in version 1071.
So essentially, whenever we do that, it goes back to that and calculates whatever the files that are needed to get that version, picks them up and notes it, right?
Yeah, essentially. Yep.
I was just trying to remember that Rational Clear Case used to have something called versions, file systems and things like that. It was implementing version control using a virtual file system.
I remember what you're talking about, like Rational Rows, you mean?
Yeah, the Rational Rows,
yeah.
those guys, yeah. The
Yeah, this
is
is
the versioning tool that they had.
Yeah, that's actually,
I don't know. But
it's the data sets that we have here are so massive that what that's actually using is file versioning. And it'll actually look at, like, to your point, like a virtualized version of it. But what we're actually doing is these are discrete physical versions of the files.
Okay.
In a lot of the cases, you couldn't keep up with the speed based off of usually.
Yeah, I understand that it would become very computationally, and every time a kernel call would need to be done, so it might become very expensive to do those things.
Exactly. That's actually, so in this case, it's actually just the logging structure and physical actual files. So a couple of the, I'm just going to expand this out all the way. Sorry. Limitations on this. And the main one is associated to this vacuuming. Sorry. Vacuum is a function that you can either allow Delta to do automatically, or you can actually that you can do programmatically if you want it as well. And what vacuuming does is it actually it will say, because these things will start piling up, right? Like there's a lot of stuff that can be in there. And the limitation of time travel is that the data that exists has to be in that, in the file system, and you do want to clean these out from time to time. So what we have is a default set of vacuums that actually will vacuum up based off of other actions on the file set for a Delta table. And that is usually, I think, around a week's worth of data. You can make that longer or shorter, but we do advise that you actually don't do this at month-long sets, just because the storage can get expensive.
I'm sorry. What does vacuuming mean in this context?
It literally it's a action on a Delta table. It'll say vacuum to a number of hours in the past, and it will literally go look at the log structure, and it'll say, okay, for everything past 72 hours, or or a week's worth of time, essentially get rid of all of those all the data that is too old and that we don't need around anymore. Did that answer your question?
Yeah. So it's basically like removing the pointers to that old version, and only the current, or what's left, is there.
Yes, and then and if there's old remnant files, get rid of them, because I don't want to keep them around anymore in S3. So we don't actually think, we don't advise people to use this time travel for months or years, because it can get very expensive. People can, but we don't advise people to do it in that manner. The other cool feature that this allows for, these versionings allows for, is clones. So think of this like where you could actually, and clones are either deep or shallow. A shallow clone is essentially, you say clone my table at version X, and that as clone X or some other table name. And what that clone is it's just a point in time reference to that version at that point in time. And it's just really a pointer, kind of like a view would be a pointer. And it's so that you can reference it easily. A shallow clone, just like vacuum, actually has to be there to exist. A deep clone will do a full clone of a table at a point in time. So if you want to say, clone this table at version Y, it will actually make a full copy of that into a different folder structure and at that version and time, and copy it over, so that you can, let's say for the time travel ML use case, that's another case where you actually take a point in time reference and copy it over so that that can actually be done for years at a time. And you can keep the version at that given time forever or whenever you want to delete it.
So time travel can be both like bidirectional, it can do undo and redos.
No, time travel, well, you can go back and revert to a version. You can do that as long as that version's still there. So I guess you can actually go back in time and revert to a version. I actually don't know if you can then go back to today's version or not, quite frankly. I think you still can as long as it's not vacuumed up.
Thank you.
Yeah, no problem. So other things that other features that are huge for this is essentially updates and deletes and something called a merge statement. I think everybody probably has seen an update and delete statement, but in big data land, updating at a row by row basis is very hard to do, and in certain cases impossible if you're actually streaming data in and out of it concurrently. What we allow you to do with Delta tables are update just like you would at a regular database at a row by row basis, and you won't actually incur any problems that are associated with data corruption and big data by trying to do the same thing in a big data setting. The same is possible with deletes. I want to actually, I'm just going to go through to show you what a merge statement is. This is actually, since I would imagine some of you might not have seen a merge or an upsert statement. What these statements are is it's essentially an append or a copy into statement into a table on a condition. And you can have multi conditions where you can say delete based off of this condition, update based off of this condition, or insert based off of a third condition. And this makes it very powerful so that you can have all of that all in one place. And you can actually also do that in a streaming manner so that you can actually stream in and out of these tables, or actually in this case, into these tables, and have one big statement that actually defines how you want to prepare that table based off of the conditional values coming in. It's pretty powerful and also very compact. And a lot of our customers will use the merge statements when they're augmenting Delta tables. I know that this is probably a new concept, so I just wanted to see if anybody had any questions before moving on. Okay. All right. So for the next piece, and this is also a product of the ability to actually go through versions. You can stream in and out of these tables extremely easily, and without really setting anything up, especially out of the tables, because you can use it as a source, just like you would use Kafka as a source of a stream as well. And that idea is pretty powerful, and it's actually something that I'll get into afterwards, where you can set up multiple versions of these tables that have manipulations in the middle, and like in a what we call a medallion architecture, where it's bronze, silver, and gold. And you can have different small manipulations over the course of time into these different stage tables. And that last stage table is usually a aggregated table or a feature set table that would be used in ML. The first piece of this, though, is data skipping and how you can actually use these formats as to prune out the values that you don't want to actually look at. So again, think of, orders of like just extremely large amounts of data, and these large amounts of data are in a larger number of specific files as well, and partition pruning can make it so that you can actually skip different pieces of that, particularly using the partition columns. If you have partition columns, it won't ever have to actually interrogate any of those columns that are not in where statements outside of the engine. You can just look for the values that you need at any given time. There's also ways that you can also then do that off of the statistics themselves. So the metadata also includes statistics of the files themselves, and they'll give in the metadata. This is an example of what you may see in as a statistic in there, where you can have min-max values, column values that you can then use those to more granularly determine which file or which files you don't need to look at, and to find the data that you need. There's also another piece external to this that is proprietary to Databricks implementation of Delta tables that allow you to do the same idea of skipping inside of high cardinality columns called Z ordering, so that you can actually get to identify the exact area of a file in Parquet that needs to be looked at for exact values. Before going, I'll stop for a second before I go into the next piece about streaming and joins. Do you guys have any questions about that as well? Or should I go to the next set? Okay, I'll keep going. Sorry, Thomas, I just expanded enough to see what TG, aka Thomas, stood for. So I will call you Thomas from here on out.
It's all cool. I was just being a smart aleck.
I know. Okay. So streaming is another big thing, as I had mentioned, and this essentially allows you to incrementally go through the changes that happen, and you can identify where you stopped in a Delta table for those streams. That in itself is a pretty powerful idea, but matching the stream to a static Delta table, where that stream can continually come through, and that static Delta table can actually change and identify where that change happened, and then retrofit the join to that streaming table. This is something that I don't know anywhere else in the world that you can actually do this, but that is something that you can actually do in a Delta table, where you can actually have a static to stream join where the static table can change, and then manipulate the join appropriately based off of that change in the static table. What I mean by that is, like, this is actually this comes in handy when you're joining a stream to, like, say, a fact table that can actually change over time. That fact table can change, and the identified change can actually be seen, and the stream can actually continue to go without any interruption. It's actually it comes in really handy for lots of our customers that want to do continuous streams off of essentially tables that may change on the side without identifying that it needs change or physically stopping a stream to actually make the change before restarting it. This is just something, again, that I like. A lot of my customers actually found this extremely helpful over the course of time. So does anybody have any questions about any of this so far?
Hey, John, is the stream emptied when a merge happens?
To the streaming table or?
To the streaming table, yeah. So when you're joining the streaming table to the fact table with a merge, is that when the streaming table emptied?
If the merge happened on the static table, yes, and it's actually not emptied. It's just identified the changes that need to be made, and the joins will appropriately update based off of that. And keep in mind that this is still like on a streaming table it's literally coming through, right? And when that new join happens, it would identify those changes and then use it in that next set of micro batch services.
And those markers are made from the merge command, right?
Merge or update.
Gotcha. Thank you.
Yeah. All of these different pieces, plus a couple things in structured streaming in Apache Spark itself, allow us to actually build out fully functional incremental ETL architectures. And what I mean by that is a fully functional ETL architecture where only the data that has changed will actually flow through the system. This is definitely something that, if you've dealt with conventional databases, or conventional databases or data warehouses, it may be state of the art. It probably isn't. Golden Gate has been around for a very long time, but it's something that you can do now. The streaming mechanism is actually hard to do still in data warehousing, but this is something that is fully realized with the ability to use both Delta and also Spark. A couple pieces I just wanted to point out of how these things work together. The ingest is usually either a streaming technology such as Kafka or Kinesis on AWS, or I would call them file or queuing types of technologies. We have something called Autoloader that is a file-based streaming ingest, or SQS, another AWS technology that allows you to queue up folders on S3. This ingest can either be continuous, that would be a 24/7 type of stream, or scheduled. And this is something that a lot of you that may actually be used to doing streaming types of technologies, you can actually turn these off when it's finished at a given time. What I mean by that is you can actually do something called trigger once, where you can essentially say, like, okay, I want to run everything at the top of the hour that has come through since the last time you've actually run the state. And if you see anything new, transform it. If you don't, or when you're done actually seeing new things, shut itself down. And then we'll just do it again in the next hour, or we'll do it again in the next day. And that allows you to actually do a couple things. You can save all the state internal to these tables and not worry about that as a problem when you actually turn off ETL. You can also, it's a lot cheaper, because if you don't need these to be up all the time, you can actually, and you can incur and you can in your business incur latency. You can essentially just say, I just need it every hour, and it's only going to run for 5 minutes. So I only want to pay for when it's on, and it can be extremely efficient, because then also only the pieces that change actually go through the system. The structured streaming pieces of this that we actually didn't discuss here is around the state or the checkpoint that's associated to writing out where you stopped. In this case, like when you think of the versions of the Delta table, that's actually what you're writing out in the checkpoint. Is you said, I evaluated and wrote everything up to checkpoint 1072. I'm going to shut myself down, or God forbid it actually shuts, something goes wrong. You actually know that last place, that last atomic place that you actually stopped at any given time. The other piece that I just mentioned is actually the trigger ones. The Delta part of this is around essentially the ACID transactions. Again, that's actually each one of those version is associated with an atomic acid transaction that happens. Each one of these can, each table can is very easily used as a source and a sink of streaming. And then also, of course, the schema enforcement and also the evolution. Let's say you have a set of IoT logs that are coming in constantly, and you just brought on a new type of machine. You can still actually take that in, interpret what's coming in, and then identify the changes and write them out in real time and continually. I'm going to stop there, but does anybody have any questions? I can also go back. I know that I kind of went through that last part very quickly. We can go back to the ETL architecture as well, but does anybody have any questions?
Yeah, I guess for getting started with Delta, how would you, I guess, suggest like getting a workload to migrate to using Delta, or like what your, I guess, migration strategy, quote unquote?
Oh, good point. If I would say here, I'll go back to something that kind of illuminates this. Usually what we see is people using Parquet and using Spark. This isn't necessarily the only way that you can do it, but if you are using Spark, the switch over from using Spark to and any of the formats that Spark can employ, the movement to Delta is very easy, and the movement to from Parquet to Delta actually can be done in line. What I mean by that is there's actually a convert to Delta for Parquet, where you can actually just say, this folder is a Parquet table. I want it to be a Delta table, and all it really does is just understand what's already there, and then plops a log on top of it. So that's usually the first place is where people are already using Parquet and Spark and move over in that manner. Other ways are physical reads, usually in Spark, again, and then writes out to that to a Delta table to a different place. There are other connectors that can be used as well, though.
Thanks.
Yep. Anyone else?
John, my team is not having had experience with data warehousing, not having had experience with streaming. they're not really bought in yet to Databricks, and I'd like to, show them the power of Delta and Delta Lake. Do you guys have examples that are like, there's public domain data streaming that you've built, like a Delta Lake example off of?
That you can use? I'm trying to think. I actually built some of these. The streaming ones are pretty tough. What technology do you guys, are you in the cloud currently?
Yeah, we're in Azure. I've been using Databricks for about 6 months.
Oh, you have? Okay. And what does your team do now? Like what I mean by that is it a, what technologies do they use? Is it a data engineering team or is it an ML team? Like what?
Not so much ML. They're analytics, mostly public domain, although we do acquire some commercial data, but it's not streaming as of yet.
Okay.
Some census data, things like that. But they're just, so far they haven't bought into, and I have, because I have that background, the kind of time travel type stuff and the SQL merge and all that stuff. But
usually for the streaming piece, it's tough to recreate. If you're on, the reason I ask is that there is, I've only seen this being used, so I don't know where to find it, but I know that there is a, there's like an IoT hub, like recreation of data that allows you to stream out of that. I would say that the easiest of these technologies to at least like to kind of fake a stream is with autoloader, because you basically can just say point at this folder and you can actually pump data into it and it will identify and it will automatically actually pick them up and build a stream off of the data, that the new data coming into a particular landing zone. I actually have some cases out there in if you look up my name and Databricks, the last couple blogs that I wrote are on autoloader. And generally speaking, what I will do with the autoloader data is take data sets that we have available in every workspace and kind of manufacture a data set, or manufacture them to be streaming. So what I mean by that is, or the reason I mention it, and you mentioned public domain, most of the data that's actually out there that's in those data sets are public domain data. On Azure specifically, you can manufacture that type of data using the Azure data sets, I believe is actually what it's called. And I actually did a couple webinars where we actually use those data sets to show how you could use autoloader or the static version of it called copy into to take those data sets. We used weather data and taxi data to stream in, and then basically do like show that you could using machine learning indicate if rain made it more likely to get a cab in New York City, basically.
Cool.
I have one question about the time travel thing.
Mm-hmm.
You mentioned that time travel, the problem with that is that the vacuuming and things like that, and there will be too many files. So I was just wondering,
Mm-hmm.
in practice, what is the way people use to archive data that is not being used for a long time, let's say 1 month older data, and how do they actually store it?
Well, I mean, keep in mind that the data that, like, usually in these big data systems, it's the data from all of those from that time, like from the past, is actually in the data, is in the table at the given time. We actually don't see a lot of customers deleting data. What they delete is the old versions so that it's not an exact snapshot. If you did want the exact snapshot from 3 years ago and to keep it around, this is something that like a lot of financial customers that we deal with do, is we would actually see them use deep clones. So you would take a snapshot at a given day. I have a customer that does this. They're an asset management company, and they will take a snapshot of all of their positions and all of the buys and sells at a given day, and they have to keep that around for 7 years, and they do that monthly. And they use.
Oh, so you mean when you do a deep clone, you only clone whatever data is pertinent to that stuff, that point in time, and then you can compress it or zip it and keep it as a backup?
Yeah.
Okay.
That would be if you want to keep it for longer than a month, or, I mean, you can do like time travel for a month. We just don't like it like that. Like those old files can start to pile up is the main thing, that like it can get expensive, especially if you're talking about, a table that is I don't know, like petabytes of data, or petabytes coming in at like on a normal interval, like that gets expensive.
Yeah, I got it, because there would be data that has been deleted in a later version and stuff like that, and it's ridiculous to just keep it hanging around. It's better to recompute a fresh table and just keep only the rows that were there at that point of time.
Yes.
Right, as I understand it. That's what you're saying.
Yeah, and that's what a deep clone would do. It would take that point in time from where it was at that time, and it would move it somewhere else. The shallow clones are good for like shorter time frames, kind of the same way that time travel is good in the same way. Something that I've always wanted to see is actually something that stays in line, but identifies like something that, like a version that you do want to keep that for long periods of time, somewhere in between like shallow and deep. Like, I don't know what it would be called, but I'd like to see something that like, just kind of puts a line in the sand, and that's where it is for the next 3 years. And, going forward, when you vacuum it up, you actually keep that one case. I haven't found a good reason or justification for engineering to make that yet, but I think that would be cool.
Hey, John, what are the benefits about pairing the Delta tables with structured streaming again?
Well, you can use the tables as, so, like usually when you're talking about streaming is, Kafka, and then you're writing somewhere. But in this case, like with Delta, you can actually use Delta not only as the sink of a Kafka stream or any of these other streams, you can also use it as the source of a stream. So you can kind of like daisy chain these together so that you have like, this can all be like a streaming mechanism that this is a common structure, and it's not usually quite as linear as this. You have like, you'd have like 5 silver tables and they're joined together into an aggregate. But what we see is you pump the raw data into a bronze table as is. And then you can actually then recreate anything in the past based off of that, since Kafka actually only usually keeps whatever it can in memory. And then we see people stream off the back end of that Delta table, or sorry, that bronze table, and clean it up into a silver. Those silver tables are usually like things like making sure that all the formatting of the dates are correct, removing values that are erroneous, all that kind of stuff. But they're still at a at a row by row level. Then you can use that silver clean data to essentially then build out either aggregated data sets. In your case, like that's probably where you're talking about like advanced analytics. And you're actually pumping out like either new or updated aggregates of, let's say, if you're dealing with census data, if you had to rerun parts of the census, or like you realize that your ETL was bad for a certain demographic or state, then what you could do is you can rerun it and re-update the silver row by row values, and then those will identify and write to the only update the aggregated sets in that gold table that need to be updated. That last piece where you're identifying the exact row set and the type of update that's being done, that's actually off of a Delta table. We have something called, it's just like CDC, but it's called CDF, and it's change data feed. And that's actually something that either can be done off of a version by version value, or can be a streaming mechanism in its own right. So you'd actually stream off of the CDF feed as opposed to the table itself. And then you can identify if it was a delete, if it was an update, if it was an append, and then do each one of those different merge statements based off of that.
Is there a pairing where the the streaming from from data lake, or sorry, Delta Lake, can be paired with Apache Spark structured streaming?
Yeah, that's a natural, that is how we do it normally. So like if we look at in this case, this is actually doing a read from what the cloud file format of cloud files is this read stream is autoloader. But if you wanted this to be a Delta table, you literally would just say format Delta and then where you're loading it from. And then your write stream would be a Delta table as well. Is that what you mean? Sorry.
Yeah. This makes sense. Thank you.
But that's how you would do it. I actually have a, oh man, hold on, I'll check. I'll be going through this structure in a very simplistic form, but this structure in a streaming mechanism on Azure. Hold on, I haven't.
Would you say though that the structured streaming in this context would be in milliseconds, but once you introduce the the Delta tables, it may slow it down because of the versioning and all those stuff?
We actually kind of say that it would keep it around, and this is actually daisy chained together, but you can safe to say that you can do the read and write on any of these in a second, I would say. I wouldn't expect it. It's not necessarily near real time, but a second is very doable. It does depend if you're doing if you're trying to do an aggregate, then that aggregate obviously will slow it down based off of actually the difference. Like you have to actually wait for things to come in to aggregate, quite frankly. So there are pieces that will slow these down, but if you're doing from a bronze to silver, you can think of it like a second is probably about a normal acceptable amount of time. And that's also dependent on the type of infrastructure that you're going to be using and also the size of your cluster. So other things come into play when you're talking about latency, but getting to some acceptable level of seconds is definitely attainable.
Thank you.
Yeah, of course. I would also say that like if you're not there now, I'd actually say start with trigger once and make it incremental. That alone, whatever you're doing now, you're probably blowing away data and then recreating it, not on a row by row basis, but like a larger set. This type of stuff, what we see like people start with this is trigger once, make it incremental. The ETL time comes down dramatically, like as in orders of magnitude. And it also simplifies it. It's also simpler to deal with things that turn themselves off than something that's running continually, quite frankly. And you can actually start to iterate through that, and then you can drop the cadence of your jobs from daily to hourly to minute, and then to continuously. That's usually what that's what I usually see, and I would suggest starting with. Any other questions? And I was going to look up the date. If you look up my name, and I think that the date is, I'm going to do a webinar on Azure specifically on December 15th. And it's going to do I'm going to do a change data feed streaming. I'm going to do it as a trigger once so that we can actually see it stop and interrogate it. But it's basically going to take data from autoloader, the ingest. We'll put it into a bronze table. It'll then do a little bit of manipulations, put it into silver, and then off of those manipulations and updates. And actually the silver table is updated. We will then interrogate those updates and aggregate into a gold table. And I'll show how to do that in a streaming manner. That's on.
Could you please share the details of that webinar? And I hope Banjo will be able to post it on the group.
Let me see. I don't know if that's gone out yet. I'm trying to find if it's. Hold on. I think there's some sort of page for it. Let me go look for it. Give me 1 second. But it may be closer to the date. Sorry.